We know that if we connect a PN junction diode to a battery with the P side connected to the negative terminal and the N side connected to the positive terminal, the diode is said to be reverse biased. A reverse biased diode allows little or no current through it. According to the IV characteristic of a PN junction diode, the current through a reverse biased diode changes very little with an increase in applied voltage, and it remains almost constant. The value of this current is called the reverse saturation current. Let us see what happens when we increase the applied voltage across a reverse biased diode after it attains the reverse saturation current stage. We observe that the current through the reverse biased diode suddenly increases for a specific value of applied voltage. This phenomenon is called breakdown of the diode. Diode breakdown occurs because a high applied voltage creates a strong electric field that results in the breakage of covalent bonds in the P region. The electrons released by this breakage of bonds have enough energy to enter the N region, resulting in a large increase in current through the diode. The emission of these electrons from the host atoms due to the high applied voltage is called the internal field emission or field ionization. The voltage at which there is a sudden increase in current in a reverse biased diode is called the breakdown voltage. A diode designed to have low breakdown voltage under reverse bias is called a Zener diode, which is named after its inventor C. Zener. A Zener diode is made by doping both the P and N sides of a PN junction diode heavily. The circuit symbol of a Zener diode is represented as shown. Although it is similar to that of a PN junction diode, the major difference is that the two small projections in opposite directions are added to the line on the N side of the PN junction circuit symbol. The pointed edge of the triangle indicates the N side of the diode, and the base of the triangle indicates its P side. Beyond the breakdown voltage, even an insignificant change in the reverse bias voltage can produce a significantly large change in the current. This implies that the voltage across the Zener diode remains constant, even though the current through it varies widely. Thus, a Zener diode can be used as a voltage regulator to convert a variable voltage input into a constant voltage output. Here is a simple circuit used for converting a variable voltage input, say, from a rectifier into a constant voltage output using a Zener diode. The input voltage is connected to the Zener diode through a series resistor having resistance R with the Zener diode in a reverse bias arrangement. A load resistance is connected parallel to the Zener diode to collect the constant voltage output across it. The current through R is equal to the sum of the Zener current and load current. If the input voltage in the circuit is increased, the current through R and the Zener diode increases. This causes an increase in voltage across R without a change in voltage across the Zener diode. This is due to the fact that beyond the breakdown voltage, the voltage across the Zener diode remains the same, although the current through it changes. On the other hand, if the input voltage is decreased, the current through R and the Zener diode decreases. This reduces the voltage across R without affecting the voltage across the Zener diode. Thus, irrespective of increase or decrease in the input voltage, the voltage across the Zener diode remains constant, which is collected across the load resistance. Hence, the Zener diode acts like a voltage regulator. The choice of the Zener diode depends on the required output voltage. Zener diodes are available with output voltages ranging from a few volts to hundreds of volts. In order to provide good voltage regulation, it is essential that the current through the Zener diode is several times higher than the load current. This is done by selecting a suitable series resistance R that ensures Zener current in the circuit is several times higher than the load current. Optoelectronic junction devices are PN junction devices which work because of the current carriers that are generated by photons. Photodiodes, light-emitting diodes, which are referred to as LEDs in short, and solar cells are examples of optoelectronic devices. A photodiode is a device that is used to detect optical signals. It is a photodiode in your TV set that allows you to operate your TV using a remote. A photodiode is a specially fabricated PN junction diode with a transparent window that allows light to be incident on the diode. We know that light consists of tiny bundles of energy called photons, whose energy in turn depends on the frequency of the light. We also know that electrons in the semiconductor atoms of a diode need to overcome an energy gap to become free and create electron-hole pairs that act as charge carriers in the diode. When photons of light with energy greater than the energy gap fall on the diode, the photons get absorbed by the semiconductor atoms, leading to the creation of electron-hole pairs in the diode. A photodiode is designed so that the maximum number of electron-hole pairs is created in the depletion region around the PN junction. We know that the depletion region has an electric field created due to the separation of static charges on both sides of the PN junction. As soon as an electron-hole pair is created, the electric field across the depletion region pushes the hole towards the P side and the electron towards the N side. Due to this movement of charge carriers, a small photocurrent is generated through an external load connected across a photodiode. The magnitude of the photocurrent increases with an increase in the intensity of the incident light. However, this change is too small to be measured in the absence of any external bias. The magnitude of the photocurrent is too small compared to the large current that flows through the diode under forward bias. Thus, the change in photocurrent with change in the intensity of light is very difficult to measure when a diode is operated under forward bias. However, the change in the magnitude of the photocurrent with the intensity of the incident light can be measured when a small current flows through the diode under reverse bias. Thus, a photodiode is always operated under reverse bias. The IV characteristics of a reverse biased photodiode for different intensities of incident light are shown here. A light-emitting diode, or an LED, is a device that produces photons of different frequencies of light. An LED is a specially fabricated, heavily doped PN junction diode encased in a transparent cover which allows the emitted light to shine through. An LED is operated under forward bias, which increases the diffusion of minority charge carriers across the p-n junction. This leads to the recombination of the electron-hole pairs, which results in the liberation of energy in the form of photons. The energy of the emitted photons and the color of the light produced depends on the nature and the band gap of the semiconductor material used in the LED. Here is a list of some semiconductor materials used in LEDs of different colors. LEDs offer several advantages listed here over conventional electrical light sources: low operational voltage and power consumption, instant on-off switching without any warm-up time, source of near monochromatic light, long life and negligible wear and tear. LEDs have low reverse bias breakdown voltages. Thus, care must be taken that they do not get connected in reverse bias across a high voltage source. Now let us consider a solar cell. A solar cell is a device that converts light energy into electrical energy. The solar panels that you see connected to solar power appliances are made of a large number of individual solar cells. A solar cell consists of a thin, flat wafer of p-type semiconductor on which a very thin layer of n-type semiconductor is grown to create a p-n junction with a large surface area. The back of the p side is coated with a metal to form a metallic back contact. The top of the n side is provided with a metallic grid contact that covers only a small percentage of the total exposed area of the cell. A solar cell works when light is incident on it from the top over the n side of the device. A solar cell works on the same principle as that of a photodiode, where incident light generates electron-hole pairs in the depletion region of the p-n junction. As in a photodiode, the holes are pushed towards the p side and electrons are pushed towards the n side due to the electric field in the depletion region of the solar cell. The holes pushed towards the p side are collected by the back contact, while the electrons pushed towards the n side are collected by the grid contact. This collection of charges makes the back contact positive and the grid contact negative and gives rise to a current when a load is connected between the two. Unlike a photodiode, a solar cell works without any external bias. The large surface area of the p-n junction in a solar cell generates measurable photocurrent, making it a source of electricity. However, just like a photodiode, the photocurrent produced by a solar cell depends on the intensity of the incident light. If we plot the intensity of solar radiation against its energy, we find that the maximum intensity radiation is produced by photons having energy equivalent to 1.5 electron volts. Thus, semiconductors having band gaps lower than 1.5 electron volts are used in the manufacturing of solar cells. Here are a few examples. In semiconductors having band gaps higher than 1.5 electron volts, only a small portion of the total solar radiation is used to produce photocurrent. Thus, such materials are not preferred in the making of the solar cells. In semiconductors having band gaps much lower than 1.5 electron volts, most of the incident radiation is absorbed by the top layer of the cell. Thus, very little radiation reaches the depletion region to produce electron-hole pairs that gives rise to the photocurrent. Hence, such materials are also not preferred in the making of the solar cells. Besides band gap, the other criteria for selection of suitable material for solar cells include high solar radiation absorption capability, good electrical conductivity, and ease of availability and cost. Here, we can see the IV characteristic of a solar cell, which is drawn in the fourth quadrant, as it does not require any external bias and acts as a source of electricity. A transistor is a semiconductor device used for switching and amplifying electric signals. A point contact transistor was invented by J. Bardeen and Walter Brattain in 1947. The first junction transistor was invented by William Shockley in 1951. There are many different kinds of transistors. However, in this module we will discuss the transistors that contain two back-to-back p-n junctions. Such transistors are called bipolar junction transistors, referred to as BJT in short. When we speak about transistors in general, without reference to any particular kind, we refer to these bipolar junction transistors. There are two types of bipolar junction transistors: the PNP transistor and the NPN transistor. A PNP transistor consists of a smaller, heavily doped P region and a larger, moderately doped P region separated by a thin, lightly doped N region. An NPN transistor consists of a smaller, heavily doped N region and a larger, moderately doped N region separated by a thin, lightly doped P region. The smaller, heavily doped region in a PNP or in an NPN transistor is called the emitter. The emitter supplies a large number of majority charge carriers that are holes in a PNP transistor and electrons in an NPN transistor. The larger, moderately doped region in a PNP or in an NPN transistor is called the collector. The collector collects the major portion of the majority charge carriers provided by the emitter. The thin, lightly doped region in a PNP or in an NPN transistor that separates the emitter and collector is called the base. Connecting terminals are provided for the emitter, the collector, and the base. Thus, a transistor is a three-terminal device. Suitable potential difference must be applied across both the p-n junctions to operate a transistor. This process is called biasing the transistor. To bias the two p-n junctions in the transistor, we require a pair of terminals for each p-n junction. Thus, in total, we require 4 terminals. But the transistor has only 3 terminals. Hence, one of the terminals is made a common terminal to bias the two p-n junctions. The emitter, or the base, or the collector can act as the common terminal, and biasing on this information, the configuration of the transistor is named accordingly. In this module, we discuss about transistors in common base configuration. During biasing, normally the PN junction between the emitter and the base is forward biased, while the PN junction between the base and the collector is reverse biased. The reasons for adopting such a biasing scheme for the two junctions will be discussed at the appropriate juncture in the course. A transistor with its emitter base junction forward biased and base collector junction reverse biased is said to be in an active state. Before we discuss the working of PNP and NPN transistors in the active state, let us recall that by convention, the direction of electric current is taken opposite to the direction of the flow of electrons, that is, in the same direction of the flow of holes. When the emitter base junction of a PNP transistor is forward biased, a large number of holes from the emitter enter the base. This large flow of holes from the emitter to the base constitutes the emitter current. This current is equal to the current entering the emitter from the emitter terminal connected to the battery. Since the base is very thin and the base collector junction is reverse biased, most of the holes entering the base reach the collector terminal, forming the collector current. Only a very small portion of the holes entering the base reach the base terminal, forming a small base current. A PNP transistor is represented by the symbol as shown. Note that the direction of the arrow indicates that in a PNP transistor, current is directed from the emitter to the base. Similarly, when the emitter base junction of an NPN transistor is forward biased, a large number of electrons from the emitter enter the base. This large flow of electrons from the emitter to the base constitutes the emitter current, opposite in direction to the flow of electrons. This current is equal to the current leaving the emitter from the emitter terminal connected to the battery. Since the base is very thin and the base collector junction is reverse biased, most of the electrons entering the base reach the collector terminal constituting the collector current. Only a very small portion of the electrons entering the base reach the base terminal, forming a small base current. An NPN transistor is represented by the symbol as shown. Note that the direction of the arrow indicates that in an NPN transistor, current is directed from the base to the emitter. As per Kirchhoff's law, in both PNP and NPN transistors, the emitter current is equal to the sum of the base current and collector current. Note that in both cases, the base current is very small compared to the emitter current. Thus, the emitter and the collector currents are nearly equal. In the circuits, we discussed so far about transistors in the common base configuration. We will discuss later about different types of configurations and their uses. You have learned that there are two types of bipolar junction transistors, namely the PNP transistors and the NPN transistors. You have also learned that a transistor is said to be in active state when its emitter base junction is forward biased and base collector junction is reverse biased. While biasing a transistor, the forward biased connection is called the input circuit and the reverse biased connection is called the output circuit. Since a transistor is a three-terminal device, one of its terminals is common to both input and output. This gives rise to three transistor circuit configurations. When the base of a transistor is common to the input and output, the transistor is said to be in the common base configuration. In this case, the input voltage is represented as VEE and the output voltage is represented as VCC. When the emitter of a transistor is common to the input and output, the transistor is said to be in the common emitter configuration. In this case, the input voltage is represented as VBB and the output voltage is represented as VCC. When the collector of a transistor is common to the input and output, the transistor is said to be in the common collector configuration. In this case, the input voltage is represented as VBB and the output voltage is represented as VEE. Since the NPN silicon transistor is the most commonly used transistor and the common emitter configuration is the most commonly used circuit configuration, let us study the input and output characteristics of an NPN transistor in the common emitter configuration. The circuit to study the input and output characteristics of an NPN transistor in the common emitter configuration is as shown. In the common emitter configuration, the input is between the base and the emitter and the output is between the collector and the emitter. The variation of base current, IB, with the base emitter voltage, VBE, is referred to as the input characteristics, and the variation of collector current, IC, with the collector emitter voltage, VCE, is referred to as the output characteristics. The input characteristics of an NPN transistor in the common emitter configuration can be studied by plotting the base current, IB, against the base emitter voltage, VBE, at a constant collector emitter voltage, VCE. The collector emitter voltage, VCE, is kept constant within the range of 3 volts to 20 volts to ensure that the collector base junction is reverse biased and the transistor is in active state. Since the common emitter voltage, VCE, is the sum of the common base voltage, VCB, and the base emitter voltage, VBE, and the base emitter voltage, VBE, is 0.6 volts for a silicon transistor, the collector emitter voltage is sufficiently larger than 0.6 volts. An increase in the collector emitter voltage, VCE, appears with an increase in the collector base voltage, VCB, keeping the base emitter voltage, VBE, constant. Thus, the effect on the base current IB is negligible. Hence, the different constant values of the collector emitter voltages, VCE, gives almost identical curves for the input characteristics. The input characteristics can be used to calculate the input resistance. The input resistance, Ri, is defined as the ratio of the change in the base emitter voltage delta VBE to the resulting change in the base current delta IB at a constant collector emitter voltage VCE. The input resistance is referred to as a dynamic resistance and is of the order of a few hundred ohms to a few thousand ohms. The output characteristics of an NPN transistor in common emitter configuration can be studied by plotting the collector current IC against collector base voltage VCE at a constant base current IB. Since the base emitter junction is in forward bias, a small increase in the base emitter voltage VBE increases the whole current from the emitter and the electron current from the base. As a result, the base current IB and the collector current IC increase proportionately. Thus, the different constant values of the base current IB give different output characteristics as shown here. The output characteristics can be used to calculate the output resistance. The output resistance, RO, is defined as the ratio of the change in the collector emitter voltage, delta VCE, to the change in the collector current, delta IC, at a constant base current IB. Since the base collector junction is reverse biased, the output resistance is very high and is of order of a few hundred kilo ohms. The current amplification factor, beta, of a transistor is defined as the ratio of the change in the collector current, delta IC, to the change in base current, delta IB, at a constant collector emitter voltage, VCE. The AC current amplification factor is also known as the small signal current gain. Its value is very large since a large change in the collector current results in a very small change in the base current. The ratio between the absolute values of the collector current IC and the base current IB is called the DC current amplification factor. The values of the AC current amplification factor and the DC current amplification factor are almost equal. You have learned that when the emitter terminal of a transistor is common to the input and the output, the transistor is said to be in common emitter configuration. For a transistor in common emitter configuration, the forward-biased emitter-base junction forms the input circuit, where the input voltage is VBB, while the reverse-biased collector-emitter junction forms the output circuit, where the output voltage is VCE. We shall try to understand the operation of the transistor as a switch by analyzing the behavior of the base-biased NPN transistor in the common emitter configuration. On applying Kirchhoff's voltage rule to the input of the circuit, we get VBB is equal to IB into RB plus VBE. Let this be equation 1. And, on applying Kirchhoff's voltage rule to the output of the circuit, we get VCE is equal to VCC minus IC into RC. Let this be equation 2. Here the input voltage VBB is represented with VI and the output voltage VCE is represented with VO. Then the equation 1 can be written as VI is equal to IB into RB plus VBE. Let this be equation 3. And the equation 2 can be written as VO is equal to VCC minus IC into RC. Let this be equation 4. Let us now discuss the change in the output voltage, VO, with the change in the input voltage, VI. In case of a silicon transistor, the cutoff voltage is 0.6 volts. As long as the input voltage VI is less than 0.6 volts, the transistor is in the cutoff state and the collector current IC is 0. Then from equation 4, the output voltage VO is equal to VCC. When the input voltage VI becomes greater than 0.6 volts, the transistor goes into the active state. In the active state of the transistor, the collector current IC increases linearly with increase in input voltage Vi. Then, the output voltage Vo is equal to VCC minus IC into RC. The output voltage Vo decreases linearly till its value becomes less than 1 volt. Beyond this, the transistor goes into the saturation state. That is, with further increase in input voltage Vi, the output voltage further decreases to 0 but never becomes 0. In the saturation state of the transistor, the collector current IC is maximum. Let us now discuss about the transistor as a switch. When the input voltage Vi is low, the transistor is in the cutoff region. In the cutoff region, the collector current IC is 0 and it is not conducting. Then it is said to be switched off. If the input voltage Vi is high enough to drive the transistor into saturation state, the output is low and very near to 0, and the collector current IC is maximum. Then it is said to be switched on. Let us now discuss about the transistor as an amplifier. To discuss the transistor as an amplifier, we use the active state of the transistor. In the active region of the transistor, the output voltage Vo decreases linearly with an increase in the input voltage Vi. If delta Vi and delta Vo are the small changes in the input voltage and the output voltage, then the ratio of the change in output voltage to the change in input voltage is called small signal voltage gain. That is, AV is equal to delta Vo by delta Vi. Let this be equation 5. When the input voltage Vi is at the midpoint of the active region, then the circuit behaves as a common emitter amplifier with voltage gain AV. This voltage gain AV can be expressed in terms of the resistances in the circuit and the current gain of the transistor. We know that the current gain of the transistor, beta AC, is equal to delta IC by delta IB. Let this be equation 6. From equation 4, we can write the small change in output voltage delta Vo is equal to 0 minus RC into delta IC, which is equal to minus RC into delta IC. Let this be equation 7. Similarly, from equation 3, the small change in voltage delta Vi is equal to RB into delta IB plus delta VBE. But delta VBE is negligibly small in the circuit. Then delta Vi is equal to RB into delta IB. Let this be equation 8. On substituting equations 7 and 8 in equation 5, we get AV is equal to minus RC into delta IC by RB into delta IB. Let this be equation 9. On substituting equation 6 in equation 9, we get the voltage gain of the amplifier as AV is equal to minus beta AC into RC by RB. Thus, the transistor in the active region can be used as an amplifier. You have learnt that when a transistor is in the active state, a small increase in the base current IB causes a large corresponding increase in the collector current IC. Thus, a transistor in the active state behaves like an amplifier. The operating point of a transistor as an amplifier is fixed somewhere in the middle of the active region. We know that the current amplification factor, beta AC, is equal to beta DC. That is equal to delta IC by delta IB. Let this be equation 1. And the voltage gain AV is equal to delta VO by delta VI. Let this be equation 2. These expressions are applicable to the transistor as an amplifier of DC voltage. Now let us look at the transistor as an amplifier of AC voltage. An AC sinusoidal wave representing input voltage VI superimposes over the supply voltage VBB for the base emitter circuit. The input AC voltage VI causes sinusoidal variations in the base current IB. The sinusoidal variations in the base current IB introduce corresponding sinusoidal variations in the collector current IC. The sinusoidal variations in collector current IC produces corresponding changes in the output voltage VO, which can be measured across the battery VCC and the resistance RC. Large capacitors are used to block the DC voltages while measuring the AC variations across the input and output terminals. Let us now derive an expression for AC voltage gain in the transistor amplifier. Initially, let us assume the input voltage VI is equal to 0, and applying the Kirchhoff's law to the output part of the circuit, we get VCC is equal to VCE plus IC into RC. Let this be equation 3. Similarly, applying the Kirchhoff's law to the input part of the circuit, we get VBB is equal to VBE plus IB into RB. Let this be equation 4. When the input AC voltage VI is not 0, we get the sum of VI and VBB as VBE plus IB into RB plus delta IB into RB plus RI. Let this be equation 5, where Ri in equation 5 is the internal resistance of the input circuit, which is equal to delta VBE by delta IB. From equations 4 and 5, we can write the input voltage VI is equal to delta IB into RB plus RI. The input voltage VI can be written as VI is equal to delta IB into R. Let this be equation 6, where R is equal to RB plus RI. On rearranging equation 3 for the output circuit, we get VCE is equal to VCC minus IC into RC. Let this be equation 7. Thus, a small change in VCE, delta VCE is equal to delta VCC minus delta IC into RC. Let this be equation 8. Since VCC is fixed, delta VCC is equal to 0. Thus, a small change in VCE is given as minus delta IC into RC. The change in VCE is equal to output voltage VO. Then, VO is equal to minus delta IC into RC. Let this be equation 9. The AC voltage gain AV is the ratio of output voltage VO to the input voltage VI. Substituting the values of Vi and Vo from equations 6 and 9 in the equation for AC voltage gain, we get AV is equal to minus delta IC into RC by delta IB into R. Let this be equation 10. We know that the current amplification factor beta AC is equal to delta IC by delta IB. On substituting the current amplification factor in equation 10, we get the AC voltage gain AV is equal to minus beta AC into RC by R. Let this be equation 11. Then the AC power gain in a transistor amplifier is equal to the product of the current amplification factor and voltage gain. That is, AP is equal to beta AC into AV. Note that a transistor does not generate power. It just uses the power from the batteries in its input and output circuits to amplify an AC signal. An oscillator is an electronic device that converts DC voltage into AC voltage. An oscillator consists of a transistor amplifier and a feedback network that extracts a part of the output of the amplifier and feeds it back as input to the transistor amplifier. A commonly used feedback network consists of an LC circuit formed by the combination of an inductor with inductance L and a capacitor with capacitance C. This is a resonant circuit that produces an output of a particular resonant frequency. A simple circuit used to understand a transistor oscillator is shown here. The circuit contains an NPN transistor in the common emitter configuration, with the base emitter junction forward biased and the base collector junction reverse biased. The input circuit of the transistor is connected to a coil T1 across terminals 1 and 2. The output circuit of the transistor is connected to a coil T2 across terminals 3 and 4. Note that coil T2 forms a part of the LC circuit used for the feedback network. Coils T1 and T2 are wound on the same core so that they can influence current in each other through inductance. The output circuit also contains a switch S. When the switch is open, the transistor cannot conduct and is in the cutoff state. When the switch S is closed, the collector current rises from 0 to a peak value as shown in the graph. As the collector current rises in coil T2, it induces a current in coil T1. Due to this inductance, or positive feedback from coil T2 to coil T1, the emitter current also rises to a peak value as shown in the graph. When the inductor current reaches the peak or becomes maximum, it stops rising further and the transistor goes into the saturation state. When the transistor goes into the saturation state, the current stops changing in coil T2 and therefore inductance or feedback from coil T2 to coil T1 stops. When the inductance or feedback from coil T2 to coil T1 stops, emitter current starts decreasing. As the emitter current decreases, the collector current also starts decreasing. The decreasing collector current in coil T2 sends a negative feedback through induction to coil T1. The negative feedback further decreases the emitter current and the collector current till both become zero. At this stage, the transistor is back to the cutoff state. From the cutoff state, the transistor moves to saturation state and back. The cycle continues, giving rise to an AC output. The frequency of the AC output voltage is equal to the resonant frequency of the LC circuit formed by the inductance L of coil T2 and the capacitance C. Since the LC circuit is connected on the collector side of the common terminal, this form of an oscillator circuit is called the tuned collector oscillator. You have already learned that when the P side of a PN junction diode is connected to the positive terminal of a battery and the N side is connected to its negative terminal, the diode is said to be forward biased. And when the P side of a PN junction diode is connected to the negative terminal and the N side is connected to the positive terminal, the diode is said to be reverse biased. You have also learned that a diode allows free flow of electric current under forward bias, but allows little or no current to flow under reverse bias. This property allows a diode to work as a rectifier. A rectifier is a device that converts alternating current into direct current. Now, let us consider a circuit in which an AC input is connected to the primary coil of a step-down transformer. A diode is connected in series with a load resistance R across the ends S1 and S2 of the secondary coil of the transformer as shown. Due to the AC input, S1 is positive and S2 is negative for the positive half cycle, while in the negative half cycle, S1 is negative and S2 is positive. Thus, the direction of voltage applied across the diode keeps changing. When S1 is positive and S2 is negative, the diode is forward biased and allows current to flow through it. Thus, during the positive half cycle, current flows through the load resistance and we get a voltage output across R as shown. When S1 is negative and S2 is positive, the diode is reverse biased and allows negligible current to flow through it. This current is so small that it is considered to be equal to zero. Thus, during the negative half cycle, no current flows through the load resistance and we do not get any voltage output across R. Here, the diode produces a pulsating voltage across the load resistance R. Since the output voltage is only in one direction, it is called rectified output. Since this circuit produces rectified output only for the positive half cycle of the AC wave, it is called a half-wave rectifier. Now consider the circuit as shown, in which an AC input is connected to the primary coil of a step-down transformer. The ends S1 and S2 of the secondary coil are connected to the P sides of two diodes whose N sides are connected to each other. The load resistance R is connected across the N sides of the two diodes and the center tap C is provided at the middle of the secondary coil. The potential at S1 and S2 changes with the AC input cycle. When S1 is positive and S2 is negative, Diode 1 is forward biased and allows current to flow through it. However, at the same time, Diode 2 is reversed biased and does not allow current to flow through it. Thus, during the positive half cycle, current flows through the load resistance R via Diode 1 and the center tap C, and we receive a voltage output across R. When S1 is negative and S2 is positive, Diode 1 is reversed biased and does not allow any current to flow through it. However, at the same time, Diode 2 is forward biased and allows current to flow through it. Thus, during the negative half cycle, current flows through the load resistance R via Diode 2 and center tap C, and we receive a voltage output across R. Thus, a combination of the two diodes produces more continuous pulses of rectified voltage across the load resistance R. Since this circuit produces rectified output for both the positive and the negative half cycles of the AC wave, it is called a full wave rectifier. Although the output of a full wave rectifier is more continuous than a half wave rectifier, it is still in the form of unsteady pulses of voltage. A more steady output can be received from a rectifier by connecting a suitable capacitor in parallel with the load resistance. The capacitor prevents the voltage from falling sharply through the load and provides a more steady output as shown.